All right, thanks. So this is going to be a very, hopefully a very hands-on talk, right? So the idea is there is a theory. Okay, you can do things, there are orthogonal polynomials and so on, but you're working on a project of your own. You have a specific objective function or a family of objective functions, and you want to minimize certain interaction on the sphere, right? So you do not care so much about the theory, you just want to try this one thing and see if anything falls out from it, right? So there are two options. Either you're working with a family of interactions, an infinite family, I should say, in which case you probably need to read Kumar and figure out the details, right? So if you have only one objective function, or okay, maybe you have 20 objective functions, then you do not need a lot of fancy theory. You can work using the 90s mathematics, right? So this is a state-of-the-art as of mid-90s. And so these are the results due to Andreev and Yudin. This is the approach due to Andreev and Yudin, as Doug mentioned. So what is your goal, right? So your goal is you have some kind of interaction that acts pairwise and points on the sphere, right? So here x and y come from some collection of points. So here this cursive C is a collection. So this is maybe some sort of x1, x capital N, and it lives in this d-1 dimensional sphere. And your goal is to minimize it. So maybe this is infimum, but more likely it's a minimum. So because you're in the sphere, this is not something of the form f of the pairwise distance, right? Because obviously on the sphere, it doesn't matter if you're working with distance or dot product. So you might just as well work on dot product like this. So you look at all pairs of points, you take their dot products and minimize. Okay. You consider this problem, and obviously you have a computer, so you can come up with a candidate, right? So what you're given at this point, in addition to this goal, is a candidate configuration. Let's say C0, right? That you would like to check is optimal. So you run some kind of optimization on the sphere. You came up with the good configuration. It looks like it's optimal, but you cannot prove it. So you would like to prove that this is indeed the best collection of endpoints that minimizes your function. So how did you come up with this candidate? Well, I recommend not using Mathematica, but rather using some kind of nonlinear optimization package, such as this one, assuming that you have a smooth function, and then some kind of a tool for automatic differentiation, right? So that you don't have to compute derivatives. So there are packages for that and so on. So you use one of these. So this is an OR Jack's PyTorch of TensorFlow. Okay, you have options. Anyway, you come up with a candidate, C0, right? How do you show that C0 is optimal? Okay, all you have to do is to consider one line of inequalities. So, let's say C star is the true minimizer. Right? This is the actual minimizer. You don't have it. You would like to show that C0 equals a C star. Okay, what can you say about this C star? Well, okay, so I just remember that Doug calls this H. So this is the H in Doug's notation. We'll try to, so my notation is the inverse of Doug's, so that's kind of awkward, but we'll try to remember about that. So this is your objective function. Let's write E sub H of C for it, right? So that means you have the obvious inequality. Energy of this H interaction of C0 is at least energy of C star. Okay. So that's the beginning of your chain of inequalities. So how are you going to estimate it? So Doug has basically explained this. So together with your minimizer, you have a collection of inner products that come from it, right? So you have come up with a discrete minimizer. So you have a collection of angles that occur in it. And angles mean inner products. So this is -1, this is 1. Let's say your interaction looks something like this. Oops. Right, so you're going to tabulate these angles in here. So let's say there are some T sub something coming in here. So there is T1, let's say -1 is T1. So your collection C0 has antipodal points. So there's T1, there is T2, maybe T3, and that's it. So there are 3 angles in C0. Right. So what you do at this stage is you interpolate your interaction. So this is the graph of H with respect to T, in case you're wondering.
This is for C star, right? C star.
Right now, the angles, okay, so the angles, we don't know C star, we just have a candidate C0. We would like to show that they're actually the same, right? So these are angles from C0. You just wrote them here like so. So you have graph of the interaction, right? It acts from -1 to 1 because that's where the dot products live. Right, and so, okay, you graphed it. Maybe it looks something like this. It can have a vertical asymptote here. Let's say it does. I'll tell you later what to do if it doesn't. So let's say it blows up at when the points coincide. So let me draw H, right? So this is H, looks something like this. It becomes vertical at 1. All right. So what you will do is draw Hermite interpolant under H. So you will interpolate H, oops, exactly at the points that correspond to these inner products coming from C0. So that's what you'll do. And your Hermite interpolant will look like this. So you will match, okay, better fix this graph. So you'll match derivatives up to order 2 at every inner point. So this is a Hermite interpolant that matches second derivative at this point. Okay, this is a terrible graph, but hopefully you get the point. So right, and then it does something afterwards. I don't care.
So Alexander, how do you know it's below the drawing?
Exactly the right question you're asking. Excellent, very good. So how do we know it's below, right? So the hope is this sequence of inequalities, we then write something like this. We hope to write something like greater than or equal Hermite interpolant of F coming from, okay, sorry, of H, of small h, that's, so it's Hermite interpolant of H at the points coming from our code. Right, so that's what we hope to say. And so here it is in black, Hermite interpolant of H at points given by G. And so G here is just an auxiliary object. I'll tell you what G is, and then I'll explain why. Yeah, sometimes it's buggy like that. then I'll explain why it stays below, right? So G here is G of t is just this auxiliary object t minus t1, t minus t2 squared, t minus t3 squared. So this is just a polynomial that shows you how to interpolate at these points. You interpolate up to order 1 at t1 and up to order 2 at these two other points. Okay, why does it stay under h, this interpolant? So if we can guarantee that it does stay under h, then this is correct inequality. Okay, so that is due to basically the last slide that Doug showed, and this is also an exercise. So let's say, recall an exercise. Right, so if you have, and I'll write up these exercises that will be part of the homework for tomorrow. So F minus Hermite interpolant. Okay, again, I write F, I mean H. It's unfortunate. So this difference, right, and this is a generalized Rolle's theorem, or mean value or whatever. Can prove it by induction. So this is, let's see, so G is, let's say, of degree n, right? So you have n conditions. Then this is a derivative of order n plus 1 of this h at some intermediate point. And this is n plus 1 factorial times g, right? So, okay, so let's look at this polynomial g. G is non-negative everywhere inside negative 1, 1, right? If you can guarantee that derivatives of h up to number of angles plus 1 with multiplicities are positive, then you know that this is greater than or equal to 0.
So here,
Yeah?
3. Is n equal 3 in this case, no?
Yes, in our case, okay, yes, in our case, n equals to 5. Yes. So this is degree of g. Right? G is just this product. Okay, so if you have an objective function that allows you to do that, then okay, you know that this thing, this part works out. So you have reached this point, right, in your line of inequalities. Okay, then you look at Gegenbauer coefficients of h, right? So this up to this point, it has only been linear algebra, right? So to construct a Hermite interpolant, you only need linear algebra. Okay,
But
the next.
Sorry, but you need some complete positivity of the h as well. That's well.
Okay, sorry, I cannot.
So you need some complete positivity or something of the h here.
Okay, what is complete positivity?
Okay, so why do you have the nth derivative positive? For general h is not true.
Well, you need several positive derivatives.
Yes,
You do not need, by the way, so that's different. So in Doug's talk, so the way it is phrased there, you need absolute positivity. So that means infinite number of positive derivatives. In general, you don't need infinite number of positive derivatives. You just need exactly as many as the degree of the polynomial.
Yeah, that's why the general theorem assumes non-negativity. That's absolutely right.
Yeah, so you will need several positive or non-negative derivatives, as many as the number of angles. So basically, it comes from the number of angles. So it's you write the number of conditions, and that's the number of derivatives plus 1. Okay, minus 1. Yeah, okay, depending which one you're looking at when you say this, right? Okay, so up to this point, linear algebra only, right? Okay, so then you expand h in okay, so let's say this is one thing that you verify, right? So you reach this point, you looked at derivatives of your objective function. It has enough non-negative derivatives. You're good to go, right? So you reach this point. Okay. Then the next thing that you check when you wrote down the interpolant, you check that the interpolant, or let's write its expansion. So it's h of hg, right? And then it's something like let's say k from 1 to okay, so this goes from 0, and then I have to think this is how many we had n conditions, right? So this I guess is n minus 1. Okay, let's see, and then there are some coefficients hk, and you use the appropriate Gegenbauers. So these are the Gegenbauers that use upper subscript d minus 3 over 2. All right, and so they are orthogonal polynomials with the measure that you get if you project spherical surface measure onto a diameter. Right, doesn't matter what they are actually. It suffices to observe that Mathematica knows them and Sage knows them. Right, that's all you need. With these two auxiliary effects, okay, you can just look up a table. You write this expansion, and then you check that hk is non-negative for k greater than or equal to 1. Okay, and if you reach this point happily, then you apply what Doug said was called linear programming, right? So this is this theorem due to I think Doug said it was due to Delsart and Uden. Yeah, so whoever it is do using that theorem, you have something like this, and then this is h0. Okay, this is unfortunate. I'm writing small h here. I guess should be write big H. So these are the coefficients of the interpolant. It's big H 0 minus n times value of the interpolant at 1. Right. This is a nice finite number, unlike for your function blows up, but the polynomial stays finite. So this is a well-defined number. Okay.
What are the little hk?
Sorry. Say that again.
What are the little hk? Are they the same as the big hk?
Okay, sorry. There were no little hk's. There were I just right. So these are the.
Move to the right by 10 inches on your right. Then there are little hk.
Yeah.
I have little hk's. That's unfortunate.
Move to the last line you wrote. Move to the right of that.
Ah, okay, yeah. These are all, yes, thank you. Very good. Right, so when you wrote the interpolant, you then expanded in this particular basis. Right? Again, linear algebra. So this step is linear algebra. The previous step is linear algebra as well. You just solve a system. Yeah, so finding the H is also linear algebra. Okay, so you reach this point, and then you just need to verify the following. You just need to see if this is equal to E sub H of C0. I guess I could write it on the previous line. No, it's fine. You just check whether this is equal to and that's it. Right. So, and if it does check out, then you're golden. Then you know that C0 is a global minimizer. Okay. So once again, you have a candidate, you write down roots, you write down angles, draw the limit interpolant, check that your function has well-behaved enough derivatives for the interpolant to stay below, check that the interpolant is positive definite up to the constant, and that's that. Right, and that, okay, then you have to compare obviously the value with the candidate, and then if they don't match, okay, then you're out of luck.
So where did this lower bound come from? The n squared?
This here.
Yeah.
Okay. Right. So let's. So this was a couple slides back. A couple of Doug's slides back. Right. So let's see. What is this expression, right? What is this? This is the sum I not equal to j. Sorry, I guess I don't use that. X not equal to y. Belong to C star h of x dot y, right? Then you use addition formula. Okay, I guess not yet. You just use your expansion over here first. Okay, this is equal to this guy here at x dot y, still the same sum. Okay, I guess I need. Oof. Something like this, right? So you just plug in the expansion, and then you use that Eigenbauers are non-negative. So you drop all of them. So that was the crazy thing that Doug said was crazy, right? So that's the crazy part. Exactly that estimate. And then, okay, so you drop all of them. You may ask, okay, where does the minus n? Okay, so this comes from you have n squared pairs, right? And you just keep the constant term. This comes from the fact that you were looking at x distinct from y, so you have to subtract the diagonal. Okay, so if you can check this, that's it. So basically, you don't need to think about designs or anything. There are two options. Either your configuration is a design of sufficient, sufficiently good quadrature, or it isn't. But you just verify the inequality. That's it. You don't care about anything. So either it works or not. So let's do it. Okay. So let's do this now. Exercise. Oops. Which we will actually do in the remaining, I think, 15 minutes. So I'll go. Okay. We'll see. I'll try to go to do fewer than 15, but we'll see. Maybe I'll have to go 15 if you don't mind. I realize these 15 minutes are all that stand between you and lunch, which puts a lot of pressure on me.
Oh, but this is very entertaining.
So exercise, octahedron. Okay, I'll tell you what octahedron is. So if you take 6 electrons, well, it's pretty hard to do, but let's say you take 6 electrons or something like that, and you put them on a conducting sphere. So the claim is that they place themselves at the vertices of regular octahedron, which I will now try to draw. So this is for n equals 6, right? So the claim is of all collections of 6 electrons, octahedron is the best. Okay, what is octahedron exactly? And again, you can, in principle, come up with this candidate numerically, right? Using your computational package of choice. Okay, I cannot clearly draw a straight line, so we'll try with the ruler. Okay, so it's a square bipyramid, if you like that better. It's a square bipyramid, and it's regular so that all the edges are equal. And it's it's rotational invariant, so no matter which angle you look, from which angle you look at it, it's the same. So also, I guess I need to tell you what Newtonian potential is. Okay. And then there's this semi-invisible edge, which nobody can see. All right. So the claim is this is the best configuration, and there is a sphere around it, right? So this is the best configuration inscribed in, let's say, unit sphere. So I guess I'll say this on the unit sphere. All right. So let's go ahead and do this. So I did part of the work for you. So I gave you the candidate. I'll write down the potential for you as well, right? So what is the potential? So F, okay, not F, H, to remember. H of T is up to a scalar multiple is this. Right, so you just use the law of cosines and so on. So what is Newtonian potential? I'm just taking the inverses of distances and add them up. Let's say C6 or something. So you have a code of cardinality. You have a collection of cardinality 6. You let it move around in the sphere. This is the potential. And of course, the claim is that these two are the same, right? But this is potential in terms of the inner product, and this is potential in terms of the distance. So obviously this is not correct because there is still a constant factor, but doesn't matter for minimization. Okay, so this is your candidate. What are the angles in this configuration? So remember, we need angles. What are the angles? So pairwise angles that you can get in here. So here's the center of your unit sphere, right? You take little radii, right? So what are the angles that you get? Okay, I didn't hear anything.
Multiples of I half. Alex, they're answering.
Okay, I hear people saying things. I'm assuming they're correct, but I cannot discern the words. So, okay, good. Yeah, so what you said is correct, obviously, because you know the answer. So okay, so the only scalar product that we care about is a 0, right? So that's yeah. Well, okay, and -1, I should say there are 2, right? So let me draw the thing for you, right? So what are the conditions for our interpolant, right? So let's write them down. Interpolant at let's call the interpolant H2, right? Because as you can recognize easily, it's going to be degree 2 polynomial. We have 3 conditions for it. Okay, it has to touch a function there, and then it goes up or something like this. Okay, this is obviously a terrible picture, but bear with me. Yeah, I guess it's a bit too terrible. It's increasing. Okay.
That's fine. Don't worry.
Well, I feel bad about such a terrible interpolant. So you see, there are 3 conditions. which you can satisfy by a polynomial of degree 2. You write down the conditions. At -1, it has to be 1/2, right, to match your function. Then it has to match also the derivatives at 0, I guess. So it has to be this, which is what, 1, and then it has to match the derivative. And again, this is in the algebra. You solve, you write your polynomial, you solve it. Okay, you're done. Then you use Legendre polynomials, which are the Gegenbauers in two-dimensional sphere. So I think 1/2 is what I get. All right. So I'm going to write the answer for you. So I'm going to write expansion of this interpolant in Legendre polynomials. Right. So the PI's are going to be Legendre polynomials. Again, you can just look them up or ask Mathematica to produce them for you, or Sage, if that's your favorite computer algebra system. And here's what you get. So you have so I want you to keep to pay close attention to these coefficients and tell if you notice anything conspicuous about them. So these are the coefficients that stand at the Legendre polynomials, right? So these are Gegenbauers. What is so conspicuous about these coefficients? Right. So again, I do some linear algebra and I expand my interpolants in terms of so I don't know if this is legible. Tell me if not. Also, this is a constant, obviously. So yeah. So I should maybe mention that we are using Gegenbauers, which are 1 at 1. So this is the standard normalization you use in this business, just a matter of convenience. Anyway, so what's so special about these coefficients? Can you make any observations about them? They're positive. Very good. Okay, so it seems that we are on the right track, right? So we can go in our line of inequalities. We have reached this stage, so we can successfully write this part. And then the remainder is just to check if we have match in here. So what remains for you to do is to compute Newtonian potential of this square bipyramid and check if this equality holds. This equality here. Yeah, so you'll just need to plug in. Okay, so this is H0 for you. Right, this is H0, and when you plug in 1 into this expression, the Gegenbauers are just 1s. Okay. So I guess we have 5 minutes, so please go ahead and check this. So remember, the interaction is this with H. 1 minus t. That's right.
You need to put square root of 2 here, otherwise.
So
if you have a factor of square root of 2 at the denominator of h, otherwise what you wrote before doesn't look right.
yeah, so okay, so when I drew this figure, I used this guy, right? Yeah, but okay, if you obtain the correct answer up to square root of 2, then it means that you just have to check carefully which whether you use this interaction or that interaction, right? Because these are, like you said, differ by a factor of square root 2. Okay, but apart from that, the two bounds match. And that's it. We're done. Octahedron minimizes Newtonian potential in the sphere. Okay, so you just need to verify one line of these inequalities. You don't need to think about checking if it's a design or it's not a design. Okay, things worked out fine, so you can, continue with your project, and the optimization part is done. Now, okay, some remarks in the remaining 3 minutes. So you may ask, okay, very well. Now, what if my interaction does not blow up at points that are close by? So if, let's say, h of 1 is less than infinity, you need a negative derivative. So I'll write down some homework examples where you will see how this can come up, right? So in Kohn and Kumar, they just say use absolutely positive functions. So all derivatives are non-negative, but they're also interested in Riesz interactions. They're interested in interactions where a point never interacts with itself, and so that means they never need to interpolate at 1. So if you think back to our interpolant, you can see that we did not interpolate the interaction at 1. If you have an interaction that does not blow up, you may have to do that. So you may have to do something like this, and that messes up your Rolle's generalized Rolle's theorem and so on. So there are some slight tweaks you may need to apply. Okay, so here's another exercise. Icosahedron is optimal for n equals 12 Newtonian potential. Right, and these results are basically due to Andreev and Yudin and so on. So they just sort of adventured into this world of different potentials, and they tried a bunch of things, and they found these different results, which were later generalized by Kohn and Kumar to a family of potentials. So that's basically the distinction, right? One objective function versus an entire family. And finally, one last caveat. So things, so I'll post some more interactions for which things work out nicely, and you can prove optimality and so on. But the main caveat is that things are generally nice only for nice configurations. Right, and that's where the entire theory of quadratures and so on comes in. So as Doug explained, there are some configurations which integrate polynomials on the sphere. And so basically things work out only for these super nice configurations. But okay, that's the bad part, because you can say, but what about everything else? How do I prove optimality of anything else? Well, the answer is generally you don't, right? But the good part, though, is whenever you optimize anything reasonable, it's almost bound to find something like a icosahedron, right? A icosahedron is just too good not to optimize anything you can think of, not necessarily an absolutely positive function or anything like that. It just optimizes anything you can think of, right? And if it doesn't, well, then you're out of luck. Then you have a bad interaction. Then you have to think about other means. So basically, these are the limitations of linear programming. And I think I should stop here. So thanks a lot, and enjoy your lunch.
Thanks a lot. Just in time, because exactly everything is ready for lunch exactly now. So
Okay, great.